Hi everyone, in this video we're going to be talking about related rates. Before we get started in your notebook, I just kind of wanted to give you a quick visual example for what we're going to be looking at. So I've just got this square here, and if I asked you to tell me things about the square, you would probably tell me it has length, it has width, and it has area. And all three of these quantities are related because length times width would give me area. Well, what happens if one of these starts changing? For example, if they both start growing, if the length and the width start getting longer, so like if I'm changing both the length and I'm changing the width, well now suddenly I've got a lot more area, right? So this should yield some kind of change in the area. But it doesn't necessarily have to be proportional. For example, let me undo a bunch of that so it goes back to the way we started. Oh, it's going to get, oh well, who cares? You know, for example, if I was to just change the width, nope, just change the width, then that would still change the area, right? So like a change in the width would still yield a change in the area, but maybe not as much. Or obviously a change in the length could do the same thing. It could somehow change the area. What we're going to be looking at today is how do all of these changes relate to each other? As you know, all of Calculus A has been about rates of change, things like slope, how quickly things are changing. And that's what we're going to talk about today, when one or more rates of change are related together. So let's take a look at your first problem here. So the side length of an equilateral triangle, okay, so I'm just going to draw my best equilateral triangle. And the side length is x, and then it has some area A. Is related by the equation area equals root 3 over 4 times the side length squared. Write an equation that relates the rate of change of the area to the rate of change of the side length. So here's the big assumption you have to make when working with related rates problems. So whenever you're working with related rates, all variables are assumed to be independent functions of time, and they're not functions of each other. So for example, in this particular problem we're looking at, let me change colors here. Is area of a triangle a function of the side length? Yes. But in this case, we're assuming that the triangle is going to be getting bigger or smaller for some reason or other. So area would also be somehow related to time. As time passes, the triangle is going to get bigger or smaller. If this annoys you, look ahead at question B, and I'm going to be asking you about how is the triangle getting bigger. We would also then assume that because the area is getting bigger with time, the side lengths would have to be getting bigger as time passes. So when you derive any sort of related rates equation, you're going to have to do so implicitly. So I'm going to derive both sides of this equation with respect to time. So let's see, we'd have the derivative of area with respect to time. And then let's see, so my 2 would come down here. I can reduce that 4. We'd have an x left behind. And then, because x is a function of time, it's not the dependent variable here, it's the independent variable. We have to chain rule this. We have to leave behind a measure of how x is changing with respect to time. And then again, like I said, you can clean this up just a little bit. Root 3 over 2 x times dx dt. So this here is telling us how the area changes of this, how the area of this triangle changes is directly related to two things. It's directly related to the side length, that's regular x. So how big the triangle is right now determines how much the area is changing, as well as how quickly that length is changing. Side. And that's our dx dt. So both of these factors combine to give us some measure of how the area would be changing. Again, if this triangle happened to randomly be growing or shrinking. Don't you just love calculus? I promise, I don't know. My favorite, like, actual real example of this style of problem is like freezing ice or something. Obviously not in a triangle, but maybe in a cube or in a sphere. So we'll look at some of those problems later on. So let's put some numbers to it. Item B says, okay, suppose the side length is increasing at a rate. Okay, so side length is increasing at a rate of 2 centimeters per minute. So that is how the side length is changing. So that sounds like my dx dt is 2 centimeters per minute when the side itself is a length of 3 centimeters. So when the length of the side is 3 centimeters. So that sounds like at this moment in time that we're looking at, x itself is 3 centimeters. And then the question is, at what rate is the area of the triangle increasing? So that sounds like we're looking for dA dt equals question mark. So thankfully, we already came up with the equation for dA dt. So at this point, we just got to plug the numbers in. Let's see, we said the side length x is 3, and then it's changing at a rate of 2 centimeters per minute, which at least we're left with something not so terrible here. 3 root 3, you can punch it in the calculator if you want. And then we got to talk about units here. So let's see, if it was just area, area is usually some length squared. Well, it should be some length squared. So in this case, it would be centimeters squared. But since it's how the area is changing with respect to time, units for dA dt would then be centimeters squared per, what would we use? Minutes? Yeah, we use minutes in this problem. So centimeters squared per minute. And again, you have to make sure the per minute is in there because it's some rate of change here. Okay, let's turn the page. Okay, so in this problem, we've got a balloon. We're going to assume it's spherical just to make things a little bit simpler. Even though I know balloons are, well, they're balloon shaped, if we're being honest. It's inflated with helium so that the radius is increasing at a rate of 2 feet per minute. Okay, so right off the bat, we've been given some information about how the radius is changing with respect to time. That is 2 feet per minute. And then we've got 2 questions here. How fast is the balloon's volume increasing at the instant that the radius is 8 feet? Okay, so when r equals 8, how is the volume changing? And since it says how is the volume changing, I'm looking for dV dt. Let's see. For these problems, I believe College Board either gives you the formula if it's something really annoying, some like really annoying geometric shape, but for the basic things, like you should know how to get to the volume of a cube or something. As for the volume of a sphere, the volume of a sphere is 4/3 pi times the radius cubed. So if we simplify that, V is 4/3 pi r cubed. Now we want to talk about how the volume is changing with respect to the radius over time. So each of these are probably going to change independently of each other. Well, how about this? It's not necessarily directly proportional. So let's go ahead and take a derivative of both sides of this equation with respect to time. So we're left over with dV dt, so how the volume changes is related to 4/3 pi is a constant. I'll bring the 3 down here. And then leave r squared behind. These will reduce. But again, you have to assume, like we said on the previous page, every variable is a function of time. So the volume, well, yes, volume at an instant is related to the radius. How the volume is changing is related to how the radius is changing. So we do have to leave behind some measure of how the radius is changing with respect to time. So let's see if we have enough numbers here to crunch this. We want dV dt. We have 4 pi, which is a number. We got a radius. I believe it's 8. Yes, it is. And then we are told up above the radius is changing at a rate of 2 feet per minute. So let's see, 64 times 4 times 2, well, really 64 times 8, I believe that's 512, and then we got a pi in there. And then let's see, our units here, our length were feet, so our volume then should probably be feet cubed. And then for time, we've been using minutes. So the rate of change of the volume in this particular case would be 512 pi feet cubed every minute. So maybe it's better to say this is a hot air balloon rather than a regular balloon. Or maybe we're just not actually filling it up for a full minute, because that's a lot of air, right? The follow-up question is, how is the surface area changing at that instant? And when it says at that instant, that means we're going to like reuse the information of r being 8, dr dt is still 2. But now we're talking about surface area, we're not talking about volume, so we got to go back, we got to figure out a new equation here. This is one you could probably just Google. The surface area of a sphere, if you don't remember it, is 4 pi r squared. And maybe I should just say S instead of SA, just because I don't want to confuse you when we take the derivative. So let's say surface area is 4 pi r squared. And to figure out how these change with respect to time and each other, whoops, that should just be d over dt, I'm sorry. Let's take a derivative of both sides. So let's see, the 2 and the 4 come together to make 8 pi r, and then r changes with respect to time. So now we got the numbers. Let's evaluate. The surface area changes at a rate of, let's see, we said the radius was 8, this was 2. So 8 times 8, 64 times 2, 128. 128, still got the pi. And then let's see, it's an area this time, so that would be feet squared, and we were still working in minutes. All right, let's turn that page. Okay, main idea here. For anything, any quantity that is changing in the problem, you have to give it some variable, and then that variable is assumed to be a function of time. So if a quantity varies throughout the problem, you must assign it a variable, and remember that variable is a function of time. And it is a function of time. So it will have a chain rule when you drive it. I bring that up because in this particular problem, there is a quantity that does not change. So let's take a second to read through it real quick. A car is 2,400 feet directly south of Curious George. Car is traveling straight west. At the instant when the car is 4,000 feet from him, it's traveling at 44 feet per second. Find the rate at which the distance between George and the car is changing at this moment. Okay, I'm a diagram guy, so let's see. We have George, and then we have a car, 2,400 feet directly south. So here's our car. And the car is traveling due west. Okay, so it's going this way. And, okay, so as time passes, it would, whoops, got rid of my car there. As it passes, it's going to go, somewhere over here. So it looks like it's going to make some kind of triangle. The question talks about the distance between George and the car after it's driven west. So I think we're actually going to be looking at it when it's over here. Because it sounds like, so okay. How do I want to explain what I'm thinking? There are two quantities in this problem that are going to be changing. How far the car has gone west, so maybe, I don't know, let's just call that x because it's a left or right idea. And the diagonal distance between the two. So I don't know, let's call it z or something. And as the car continues to go this way, go this way, go this way, that x distance is going to get longer, and that z is going to get longer as well. But they're not going to get longer at the same rate. Haha, the rates are related. Let's see. So what else do we know from the oh, and then one thing I'd like to point out to you, again, this 2400 is not changing because it's not, the car isn't going north or south. So this actually means you don't have to assign it a variable. So doesn't need variable. So then let's come up with the relationship between all the information here. We know the Pythagorean theorem. So the horizontal distance squared plus the 2400 squared would give us z squared. And in the end, we want to get to the rate at which the distance between George and the car is changing. Okay, so in the end, we want to get to dz, that was weird, dz dt. Stop. I must be hitting something with my palm that makes it do that. I don't know. So we want to get to dz dt. We know a couple other things. We know, let's see, at the instant, okay. So we know we're looking at the specific time when z is what? This would be 4,000, right? So when z is 4,000, the car is traveling at 44 feet per second. Well, the car is going west. So that sounds like our dx dt would be 44 feet per second. So why don't we go ahead and derive this? Let's see what we end up with. I think that's all we're going to get out of the word problem. So let's derive both sides with respect to time. Let's see. So we'd have 2x, then chain rule, how x is changing with respect to time. This number here is a constant, so its derivative is 0. And that makes sense because we said the car is only going west. It's not going north-south, so we shouldn't have any sort of dy dt in there or something. And then over here we'd have 2z, and again, how z is changing with respect to time. And at this point, we should just be able to plug in, right? Okay, so we got our 2, we got our x. Or do we? Oh no, we need the x. That's okay. We have the OG relationship, right? We know x squared plus 2,400 squared equals z squared. And the problem gave us a number for z. So x squared plus 2,400 squared equals 4,000 squared. So we can solve for that horizontal length at that moment in time. You do the math. It's actually one of those perfect triangles. It comes out to 3,200. So we actually are good. We know that length, 3,200. Then dx dt, we are told the car is going 44 feet per second west, so 44. And there's another 2. By the way, there's 2 on both sides, so you can divide it out. Z, let's see, we know z is 4,000. And then the question was to figure out dz dt. So all of this divided by 4,000, which should come out to about 35 and change. Okay, I know it's a little bit different than some of the other problems we've done in the past. I promise I'll work with you on setting up the equations when we need them. And yeah, I will see you tomorrow.